Now we have seen that from this description about the condition for this kind of simple harmonic motion, like the body moving in a spring, that the force is proportional to its displacement but in the opposite direction. From this definition of this type of motion, we can write down, and together with Newton's second law, we can write down a relation between the acceleration and the displacement of the body. This is a mathematical equation, and it is actually possible to solve mathematically, to work through this mathematically using the methods of calculus to get a formula for the displacement for x, to get the displacement for x. Now, I'm just going to write down the answer. I'll explain the mathematical steps later on. But first, I'm just going to write down the answer, and then I'm going to talk about how we can describe the motion. Now, the answer takes on different forms, can have different forms. Now, this is just one way of writing down the answer, just one of the words. Now, what you see here is a formula where the A there is just a fixed number, which is the amplitude, that means the maximum displacement. The sine here is a sine function, it's a trigonometric function. Now the omega is again another constant, it just so happens to be the same as the omega there. And t here is the time. T here is the time. Now if you're seeing this for the first time, it will look very abstract and it's very difficult to understand how it comes from this equation. So we'll talk about this later. But for now, let me just think about the motion itself and see how the motion might actually look like, what we get from this equation, just to have a better understanding of the physics. So if I start by thinking about plotting a graph of x against time, let's try and imagine what that would look like. So I want to plot a graph. Oops. Okay, and that's my t-axis, my time axis. That's my say x-axis or displacements. Right. So I have the spring and my little ball. I'm going to pull it down to some distance. Okay, let's say I pull it down by a distance a. So that's going to be my maximum displacement. After that, I let go. And then just go up and down, right? I pull it down here by distance a. I let go. It goes up. But when it reaches back to its rest position, it would have some velocity, right? Because as it goes up, the spring pulls at it. There is this force pulling it up, and it accelerates. It goes faster and faster and faster. So it would have a certain velocity. So actually, by the time it reaches back to its rest position, it has momentum. And because of that, it won't just stop immediately. It will have to overshoot. Right? If you want it to stop immediately, you're going to have to apply a huge force in the opposite direction, which is not there. Right? What we have is just a force from the spring, which is actually zero at the rest position. So it will overshoot, and it will go above the rest position. Now, as it goes above the rest position, you have a force that pushes it down. Okay, from the spring, pushes it down. But the momentum will cause it to keep going, but it will slow down until it stops, and then it will come back down. Okay. Now, when it overshoots, right, because the nature of the force is the same, it will actually go up and it will reach the highest point also at a displacement of a, but in the opposite direction. Okay, because the simple harmonic motion is symmetrical. So you'll go to the amplitude displacement on the other side, and then it will come back down. Alright, as it comes back down, the spring pushes at it. It will go faster and faster, and at the rest position, it will overshoot and it will come back down again. So what happens if I plot a graph of this right now? If I let it go from here, okay, if I let it go from here, it will go up. Now let's say I'm going to take my t equals to 0. I'm going to start timing at the point where it just overshoots the let's see, it's going to go up and down, right? It's going to go up and down. So at some point it will be on its way down, and it would overshoot the rest position and come down. Now I'm going to take that point where it just overshoots its rest position and continue downwards. I'm going to take that point as the t equal to 0. So let me write this down. My t is equal to 0 is when the particle, when the ball is going through its rest position, and when it's on its way down. On its way down meaning the positive direction. I'm taking the downward direction as positive. So meaning that at t equal to 0, my x is at 0. Okay, then it continues downwards. It continues downwards, meaning that the x gets more and more positive. So the x increases until it reaches a. So if I plot this on my graph, as time passes, the x increases. Okay, the x increases until it reaches a, and then it goes back up again, meaning the x decreases. So the graph should look like this, right? It goes up and then it decreases. So it goes all the way up to, right, the maximum x is a, is the amplitude, right? A is the symbol I use to represent the maximum displacements. So it goes up and come down, and as this goes back to the rest position, right, at a certain point in time, it will reach there again, and x becomes 0. So that's where we are when x comes back here, and then it will overshoot. It will go to the top. Now I'm calling my upward direction as negative. In negative direction is upwards. So when the ball overshoots and goes above its rest position, x is negative. So if I continue plotting a graph from here, that will become negative. Right, x will become negative, and the ball will go all the way up until its maximum displacement on the other side, which is here. Okay, so the magnitude of this is a, is this number a, but it has a negative sign because it's in the negative direction. So the graph would keep going, getting more and more negative until the maximum displacement, which is minus a. So that's the maximum displacement in the negative direction, and then the graph will go back to 0 again, because the ball now comes back down towards 0, the rest position, which is 0. That's the rest position, and then it repeats itself. Just keep doing this. So you can imagine that the graph must also repeat itself. It just keeps going and going and going. So there we have a graph. Okay. Now let's look at this graph a little bit. Okay, so we know that the amplitude is a, down here is minus a, and it goes to 0 there, that's my rest position, and the graph repeats itself after this time, right, from here to here to here. So this is actually one cycle. When the ball goes down, comes up and come back down, like that is one cycle. So let me write this down. So one cycle is from there to there. Right? This is one cycle. Now you can see that after this time it repeats itself because the graph here looks the same as this, and so does the motion. Right? Come down, up, like that is one cycle, and then it goes this way and this way, and that's another cycle. So the cycle repeats itself. This cycle is something that repeats itself. That's why we call it a cycle. Okay, and the time taken for one cycle. Time taken for one cycle in a previous session, I've called it T. Okay, T is the time from there to there. Time for one cycle, and it's called a period. Period is the time for one cycle. Okay, so that's what it looks like. Now, and just now I talked about how if I solve that equation for simple harmonic motion, the x is actually a sine function. Okay, I'm just going to write that down at this corner here. We have not actually proven or derived this mathematically. I'm just taking this as a formula and trying to understand it for now. Okay, so this sine function. Now, if you've learned about sine function in trigonometry, if you have seen the graph before, you'll know that if you plot a graph of the sine function, it looks quite like this. All right, it just goes up, down, up, down, up, down, like a wave. So at least from what I've done just so far is that I've not actually made use of this given answer at the moment. I've just made this graph by thinking about the motion, all right, by trying to reason out the motion and thinking about how x changes with time. So that's all I did when I made this graph. I've not made use of the formula at all. And you can see that I got a reasonable graph that looks realistic, okay, a bit jagged and irregular because I've not drawn it very well. But it does not seem too far from what you might expect from a sine function. Okay. So far so good. Now what I'm going to do next is I'm going to do something a little bit more ambitious. Now I'm going to think about how the velocity changes with time. Try that again. So that's my velocity axis. That's my time axis. Okay. Yeah. Now I want to find out, as x changes, I want to find out how velocity changes. So I want my graph to match the above graph in the time of the motion. So I'm just going to draw some dashed line just to make sure that everything, the timing is matched. Okay, so let's now think about the velocity. Right, how does the velocity change? So at the beginning, and when time t is 0, we know that x is 0, and that it is on its way down. Right, the graph shows that x is getting more positive, and we know that I've defined my positive direction to be downwards. So at time t equals to 0, the ball starts there and it is on its way down. So it's on its way down. So that means at time t equals to 0, it has a certain velocity. It has a certain velocity. Okay. Now, as it goes down, the velocity decreases. It slows down, right? Because it has to stop at the maximum displacement, at the amplitude. So we expect the velocity to slow down to a stop when it reaches the maximum displacement. Now the maximum displacement corresponds to this time, this point here. So at this point, the velocity must have come down to 0. Okay, so we got another point for the velocity. That's good. And then after that, it goes back up. It goes back up, and it overshoots. It overshoots this rest position, and it keeps going up. Now, as it goes back up, it will go faster and faster because there's this force pulling it up, right? We expect it to go faster and faster until we reach a certain velocity. But after it overshoots, this spring would provide a downward force to try to push it back down. Okay, so the ball slows down. And what this means is that at the point where it overshoots the rest position, the velocity must be at the maximum, because after that it slows down. So, and when it's on its way up, it means that the velocity is pointing in the negative direction. So if I want to plot a point for the velocity here, it would have to be a negative value. So this point where it has come back up and it's at the rest position would be this point. There. So that corresponds to this time, and at this time, therefore, I have a negative velocity in negative direction, but the magnitude is at a maximum. Okay, and after this time, it continues going up and it slows down. The magnitude of the velocity, that means the speed, decreases until it reaches the other maximum displacement point, negative displacement. And when it reaches there, and that corresponds to this point, where it reaches the maximum displacement on the negative side, and that corresponds to this time. Right, so at this point in time, at the maximum displacement on this side, again the velocity has come to 0, and then it turns back. So at that point, the velocity must be 0. Okay. Okay, let's see, where are we? Right, we are here. Okay, so it turns back and it starts moving back down, meaning in the positive direction, until it reaches the rest position again. And as it comes down, it goes faster and faster because the spring is pushing it down. It goes faster and faster, this restoring force pulling it back towards the rest position. And when it reaches the rest position, it would have reached a maximum speed again, because thereafter, it must slow down. Right, it must slow down after it overshoots, since the spring would pull it back. So it would reach the maximum speed again, but in a positive direction. And this time is this time, right, when it's come back to the rest position. So it is this time, and at this time, as we have said, it would be at a maximum speed in the positive direction. So we have these few points in the graph. And now, if I want to try and sketch this graph, let's see what it looks like. It looks like this. That's what it looks like. Okay, and that's for one cycle, and we can expect that in the next cycle it would just look exactly the same because the motion repeats in exactly the same way. So I'll try to draw the next cycle. Draw this dashed line so as to make sure that it is in time with the previous graph. So this is what it looks like. Now, if you look at this graph and you compare with this graph, you see that it is as if the above graph have shifted. Alright, it has shifted by maybe a quarter of a cycle. And if you have learned about cosine function in trigonometry, this actually looks like a cosine function which starts from 1. So, and in fact, later on, as I'll hopefully explain, the velocity is given by this formula: A times omega times cosine omega t. Right, it's actually given by a cosine function if x is given by a sine function. But don't worry about this for now. Alright, the important thing is that we understand how such a graph would come about from the previous graph, right, or from the motion given by the previous graph, and how the two graphs are related. Right, the two graphs looks very similar, except that the velocity graph looks like it's shifted to the left relative to the graph for x and shifted by exactly a quarter of a cycle. Now, in the last thing I want to talk about in this session is the acceleration. Try and draw a graph for the acceleration. So that's A. Now the acceleration, acceleration is always a bit more difficult to imagine than velocity or displacement. So let's see how we can do it. Now there are two ways to think about the acceleration. We can either think of it as the gradients of the speed-time graph, as we've learned before, or we can think of it as proportional to the force, because we know that F equals to ma. Okay, so it must be proportional to the force. It's just a fixed number times acceleration that gives the force. So if I sketch the graph, I'll expect a graph for the acceleration and a graph for the force to have very similar shape, except that the force of the graph might look higher because we need to multiply by a number. Okay. So let's see how we can get this. Okay, rather than working through this like before, which I might do later on, let me just see if I can use the fact that let me start with the graph for the velocity, and let me try to derive the graph for the acceleration using the gradients. So again, I'm just going to put the corresponding points in time so that everything is in line. Okay, let me start from that. If I start by thinking about the gradients of this graph, at this point, the gradient of the VT graph is 0 because the graph is horizontal at this point. So that means that the acceleration is 0. So that's 0 there. Now at this point, you see the slope is negative. Right? That's a positive slope. It's going to the right, but that's a negative slope. So the slope is negative, so the gradient is negative, and as you go from there to there, you see that it's getting steeper and steeper, and after that it gets less steep again. It gets more gentle again. So that is a maximum. That slope has a maximum magnitude, but it's in the negative direction. So therefore, the acceleration is a negative value. Negative maximum. Now at this point, the gradient has become 0 again because this is horizontal. So 0 there. At that point, right, the slope increases to a maximum before it decreases again. So maximum gradients, and is positive. So acceleration is positive, and there gradient horizontal, so acceleration 0. So we have our curve, or at least we can try and sketch a curve. The curve would look like this. Starting from that point, try again. Goes down, and up, and down. Okay. And because we know that the motion repeats itself, it's just going to look exactly the same in the next cycle. So that's what we have. Now, if you look at this, and if you compare with the graph for the displacement, you see that they look very similar, except that the graph for the acceleration looks like it's flipped. Is flipped upside down with respect to x. You see, whereas this peak is up, that peak is down. Okay. Now, if you recall the expression, that the formula that we obtained from the definition of simple harmonic motion, this formula A is equal to minus omega squared x. Okay, if you remember this. See, in this formula, it says that if you take x multiplied by a constant, just a fixed number, and then take the minus sign, you will get the acceleration. Now, on a graph, if you multiply by a fixed number, that usually has the effect of making the graph higher or more negative. Okay, so but the shape is going to stay about the same. Now, the effect of having a minus sign on the graph, if I multiply each x value on this graph by a minus sign, it just means that each point on the graph will become negative, which is exactly what happened here in the graph. So that point becomes negative, it comes down here. That point, which has a negative x because it's below the axis, if I add a minus sign to that, it becomes positive because minus is positive. So therefore, I have a positive acceleration here. So the minus sign that relates x to a agrees with the behavior of this graph that we have just obtained using a different way by finding the gradient of the velocity time graph. So it all fits together. It all seems quite logical, even though up to now I've not been able to explain. I've not got around to explaining why I have sines and cosines for these functions.